Chapter 4, Part 1 of The Origin of Species by Means of Natural Selection by Charles Darwin. This LibriVox recording is in the public domain. Read for LibriVox.org by Michael Armenta. Natural Selection, its power compared with man's selection, its power on characters of trifling importance, its power at all ages and on both sexes, sexual selection, on the generality of intercrosses between individuals of the same species, circumstances favorable and unfavorable to the results of natural selection, namely, intercrossing, isolation, number of individuals, slow action, extinction caused by natural selection, divergence of character related to the diversity of inhabitants of any small area and to naturalization, action of natural selection through a divergence of character and extinction on the descendants from a common parent, explains the grouping of all organic beings, advance in organization, low forms preserved, convergence of character, indefinite multiplication of species, summary. How will the struggle for existence, briefly discussed in the last chapter, act in regard to variation? Can the principle of selection, which we have seen is so potent in the hands of man, apply under nature? I think we shall see that it can act most efficiently. Let the endless number of slight variations and individual differences occurring in our domestic productions, and, in a lesser degree, in those under nature, be borne in mind, as well as the strength of the hereditary tendency. Under domestication it may truly be said that the whole organization becomes, in some degree, plastic. But the variability, which we almost universally meet within our domestic productions, is not directly produced, as Hooker and Asa Gray have well remarked, by man. He can neither originate varieties nor prevent their occurrence. He can only preserve and accumulate such as do occur. Unintentionally, he exposes organic beings to new and changing conditions of life, and variability ensues. But similar changes of conditions might and do occur under nature. Let it also be borne in mind how infinitely complex and close-fitting are the mutual relations of all organic beings to each other, and to their physical conditions of life, and, consequently, what infinitely varied diversities of structure might be of use to each being under changing conditions of life. Can it, then, be thought improbable, seeing that variations useful to man have undoubtedly occurred, that other variations useful in some way to each being in the great and complex battle of life should occur in the course of many successive generations? If such do occur, can we doubt, remembering that many more individuals are born than can possibly survive, that individuals having any advantage, however slight, over others, would have the best chance of surviving and procreating their kind? On the other hand, we may feel sure that any variation, in the least degree injurious, would be rigidly destroyed. This preservation of favorable individual differences and variations, and the destruction of those which are injurious, I have called natural selection, or the survival of the fittest. Variations neither useful nor injurious would not be affected by natural selection, and would be left either a fluctuating element, as perhaps we see in certain polymorphic species, or would ultimately become fixed, owing to the nature of the organism and the nature of the conditions. Several writers have misapprehended or objected to the term natural selection. Some have even imagined that natural selection induces variability, whereas it implies only the preservation of such variations as arise, and are beneficial to the being under its conditions of life. No one objects to agriculturists speaking of the potent effects of man's selection, and in this case the individual differences given by nature, which man for some object selects, must of necessity first occur. Others have objected that the term selection implies conscious choice in the animals which become modified, and it has even been urged that, as plants have no volition, natural selection is not applicable to them. In the literal sense of the word, no doubt, natural selection is a false term, but whoever objected to chemists speaking of the elective affinities of the various elements, and yet an acid cannot strictly be said to elect the base with which it in preference combines. It has been said that I speak of natural selection as an active power, or deity. But who objects to an author speaking of the attraction of gravity as ruling the movements of the planets? Everyone knows what is meant and is implied by such metaphorical expressions, and they are almost necessary for brevity. So again it is difficult to avoid personifying the word nature. But I mean by nature only the aggregate action and product of many natural laws, and by laws the sequence of events as ascertained by us. With a little familiarity, such superficial objections will be forgotten. We shall best understand the probable course of natural selection by taking the case of a country undergoing some slight physical change, for instance, of climate. The proportional numbers of its inhabitants will almost immediately undergo a change, and some species will probably become extinct. We may conclude, from what we have seen of the intimate and complex manner in which the inhabitants of each country are bound together, that any change in the numerical proportions of the inhabitants, independently of the change of climate itself, would seriously affect the others. If the country were open on its borders, new forms would certainly immigrate, and this would likewise seriously disturb the relations of some of the former inhabitants. Let it be remembered how powerful the influence of a single introduced tree or mammal has been shown to be. But in the case of an island, or of a country partly surrounded by barriers into which new and better adapted forms could not freely enter, we should then have places in the economy of nature which would assuredly be better filled up if some of the original inhabitants were in some manner modified. For, had the area been open up to immigration, these same places would have been seized on by intruders. In such cases, slight modifications, which in any way favored the individuals of any species, by better adapting them to their altered conditions, would tend to be preserved, and natural selection would have free scope for the work of improvement. We have good reason to believe, as shown in the first chapter, that changes in the conditions of life give a tendency to increased variability, and in the foregoing cases the conditions changed, and this would manifestly be favorable to natural selection, by affording a better chance of the occurrence of profitable variations. Unless such occur, natural selection can do nothing. Under the term of, quote, variations, end quote, it must never be forgotten that mere individual differences are included. As man can produce a great result with his domestic animals and plants by adding up in any given direction individual differences, so could natural selection, but far more easily from having incomparably longer time for action. Nor do I believe that any great physical change, as of climate, or any unusual degree of isolation to check immigration, is necessary in order that new and unoccupied places should be left for natural selection to fill up by improving some of the varying inhabitants. For, as all the inhabitants of each country are struggling together with nicely balanced forces, extremely slight modifications in the structure or habits of one species would often give it an advantage over others, and still further modifications of the same kind would often still further increase the advantage, as long as the species continued under the same conditions of life, and profited by similar means of subsistence and defence. No country can be named in which all the native inhabitants are now so perfectly adapted to each other and to the physical conditions under which they live, that none of them could be still better adapted or improved, for in all countries the natives have been so far conquered by naturalized productions that they have allowed some foreigners to take firm possession of the land, and as foreigners have thus in every country beaten some of the natives, we may safely conclude that the natives might have been modified with advantage, so as to have better resisted the intruders. As man can produce, and certainly has produced, a great result by his methodical and unconscious means of selection, what may not natural selection effect? Man can act only on external and visible characters. Nature, if I may be allowed to personify the natural preservation or survival of the fittest, cares nothing for appearances, except in so far as they are useful to any being. She can act on every internal organ, on every shade of constitutional difference, on the whole machinery of life. Man selects only for his own good, nature only for that of the being which she tends. Every selected character is fully exercised by her, as is implied by the fact of their selection. Man keeps the natives of many climates in the same country. He seldom exercises each selected character in some peculiar and fitting manner. He feeds a long and a short-beaked pigeon on the same food. He does not exercise a long-backed or long-legged quadruped in any peculiar manner. He exposes sheep with long and short wool to the same climate, does not allow the most vigorous males to struggle for the females. He does not rigidly destroy all inferior animals, but protects, during each varying season, as far as lies in his power, all his productions. He often begins his selection by some half-monstrous form, or at least by some modification prominent enough to catch the eye, or to be plainly useful to him. Under nature, the slightest differences of structure or constitution may well turn the nicely balanced scale in the struggle for life, and so be preserved. How fleeting are the wishes and efforts of man! How short his time, and consequently how poor will be his results compared with those accumulated by nature during whole geological periods! Can we wonder, then, that nature's productions should be far truer in character than man's productions? That they should be infinitely better adapted to the most complex conditions of life, and should plainly bear the stamp of far higher workmanship? It may metaphorically be said that natural selection is daily and hourly scrutinizing throughout the world the slightest variations, rejecting those that are bad, preserving and adding up all that are good, silently and insensibly working whenever and wherever opportunity offers, at the improvement of each organic being in relation to its organic and inorganic conditions of life. We see nothing of these slow changes in progress until the hand of time has marked the long lapse of ages, and then so imperfect is our view into long past geological ages that we see only that the forms of life are now different from what they formerly were. In order that any great amount of modification should be effected in a species, a variety, when once formed, must again, perhaps after a long interval of time, vary or present individual differences of the same favourable nature as before, and these must again be preserved, and so onward step by step. Seeing that individual differences of the same kind perpetually recur, this can hardly be considered as an unwarrantable assumption, but whether it is true, we can judge only by seeing how far the hypothesis accords with, and explains, the general phenomena of nature. On the other hand, the ordinary belief that the amount of possible variation is a strictly limited quantity is likewise a simple assumption. Although natural selection can act only through and for the good of each being, yet characters and structures which we are apt to consider as of very trifling importance, may thus be acted on. When we see leaf-eating insects green, and bark-feeders mottled gray, the alpine ptarmigan white in winter, the red grouse the color of heather, we must believe that these tints are of service to these birds and insects in preserving them from danger. Grouse, if not destroyed at some period of their lives, would increase in countless numbers. They are known to suffer largely from birds of prey, and hawks are guided by eyesight to their prey, so much so that on parts of the continent persons are warned not to keep white pigeons, as being the most liable to destruction. Hence, natural selection might be effective in giving the proper color to each kind of grouse, and in keeping that color, when once acquired, true and constant. Nor ought we to think that the occasional destruction of an animal of any particular color would produce little effect. We should remember how essential it is in a flock of white sheep to destroy a lamb with the faintest trace of black. We have seen how the color of hogs, which feed on the paint root in Virginia, determines whether they shall live or die. In plants, the down on the fruit and the color of the flesh are considered by botanists as characters of the most trifling importance. Yet we hear from an excellent horticulturalist, Downing, that in the United States smooth-skinned fruits suffer far more from a beetle, a circulio, than those with down, that purple plums suffer far more from a certain disease than yellow plums, whereas another disease attacks yellow-fleshed peaches far more than those with other colored flesh. If, with all the aids of art, these slight differences make a great difference in cultivating the several varieties, assuredly, in a state of nature, where the trees would have to struggle with other trees and with a host of enemies, such differences would effectually settle which variety, whether a smooth or downy, a yellow or a purple-fleshed fruit, should succeed. In looking at many small points of difference between species, which, as far as our ignorance permits us to judge, seem quite unimportant, we must not forget that climate, food, etc., have no doubt produced some direct effect. It is also necessary to bear in mind that owing to the law of correlation, when one part varies, and the variations are accumulated through natural selection, other modifications, often of the most unexpected nature, will ensue. As we see that those variations which, under domestication, appear at any particular period of life, tend to reappear in the offspring at the same period, for instance, in the shape, size, and flavor of the seeds of the many varieties of our culinary and agricultural plants, in the caterpillar and cocoon stages of the varieties of the silkworm, in the eggs of poultry, and in the color of the down of their chickens, in the horns of our sheep and cattle when nearly adult. So, in a state of nature, natural selection will be enabled to act on and modify organic beings at any age by the accumulation of variations profitable at that age, and by their inheritance at a corresponding age. If it profit a plant to have its seeds more and more widely disseminated by the wind, I can see no greater difficulty in this being effected through natural selection than in the cotton planter increasing and improving by selection the down in the pods on his cotton trees. Natural selection may modify and adapt the larva of an insect to a score of contingencies wholly different from those which concern the mature insect, and these modifications may affect, through correlation, the structure of the adult. So, conversely, modifications in the adult may affect the structure of the larva. But in all cases, natural selection will ensure that they shall not be injurious, for if they were so, the species would become extinct. Natural selection will modify the structure of the young in relation to the parent, and of the parent in relation to the young. In social animals, it will adapt the structure of each individual for the benefit of the whole community. if the community profits by the selected change. What natural selection cannot do is to modify the structure of one species without giving it any advantage for the good of another species. And though statements to this effect may be found in works of natural history, I cannot find one case which will bear investigation. A structure used only once in an animal's life, if of high importance to it, might be modified to any extent by natural selection. For instance, the great jaws possessed by certain insects used exclusively for opening the cocoon, or the hard tip to the beak of unhatched birds used for breaking the eggs. It has been asserted that of the best short-beaked tumbler pigeons in a greater number perish in the egg than are able to get out of it, so that fanciers assist in the act of hatching. Now, if nature had to make the beak of a full-grown pigeon very short for the bird's own advantage, the process of modification would be very slow, and there would be, simultaneously, the most rigorous selection of all the young birds within the egg, which had the most powerful and hardest beaks, for all with weak beaks would inevitably perish, or more delicate and more easily broken shells might be selected, the thickness of the shell being known to vary like every other structure. It may be well here to remark that with all beings there must be much fortuitous destruction which can have little or no influence on the course of natural selection. For instance, a vast number of eggs or seeds are annually devoured, and these could be modified through natural selection only if they varied in some manner which protected them from their enemies. Yet many of these eggs or seeds would, perhaps, if not destroyed, have yielded individuals better adapted to their conditions of life than any of those which happened to survive. So, again, a vast number of mature animals and plants, whether or not they be the best adapted to their conditions, must be annually destroyed by accidental causes, which would not be in the least degree mitigated by certain changes of structure or constitution, which would, in other ways, be beneficial to the species. But let the destruction of the adults be ever so heavy, if the number which can exist in any district be not wholly kept down by such causes, or, again, let the destruction of eggs or seeds be so great that only 100th or 1,000th part are developed, yet of those which do survive, the best adapted individuals, supposing that there is any variability in a favorable direction, or, again, let the destruction of eggs or seeds be so great that only 100th or 1,000th part are developed, yet of those which do survive, the best adapted individuals, supposing that there is any variability in a favorable direction, will tend to propagate their kind in larger numbers than the less well adapted. If the numbers be wholly kept down by the causes just indicated, as will often have been the case, natural selection will be powerless in certain beneficial directions, but there is no valid objection to its efficiency at other times and in other ways, for we are far from having any reason to suppose that many species ever undergo modification and improvement at the same time in the same area. Sexual selection. Inasmuch as peculiarities often appear under domestication in one sex and become hereditarily attached to that sex, so no doubt it will be under nature. Thus it is rendered possible for the two sexes to be modified through natural selection in relation to different habits of life, as is sometimes the case, or for one sex to be modified in relation to the other sex, as commonly occurs. This leads me to say a few words on what I have called sexual selection. This form of selection depends not on a struggle for existence in relation to other organic beings, or to external conditions, but on a struggle between the individuals of one sex, generally the males, for the possession of the other sex. The result is not death to the unsuccessful competitor, but few or no offspring. Sexual selection is, therefore, less rigorous than natural selection. Generally the most vigorous males, those which are best fitted to their places in nature, will leave most progeny. But in many cases, victory depends not so much on general vigor, but on having special weapons confined to the male sex. A hornless stag, or spurless cock, would have a poor chance of leaving numerous offspring. Sexual selection, by always allowing the victor to breed, might surely give indomitable courage, length of spur, and strength to the wing to strike in the spurred leg, in nearly the same manner as does the brutal cockfighter by the careful selection of his best cocks. How low in the scale of nature the law of battle descends, I know not. Male alligators have been described as fighting, bellowing, and whirling around like Indians in a war dance for the possession of the females. Male salmon have been observed fighting all day long. Male stag beetles sometimes bear wounds from the huge mandibles of other males. The males of certain hymenopterous insects have been frequently seen by that inimitable observer, M. Fabre, fighting for a particular female, who sits by, an apparently unconcerned beholder of the struggle, and then retires with the conqueror. The war is perhaps severest between the males of polygamous animals, and these seem oftenest provided with special weapons. The males of carnivorous animals are already well armed, though to them and to others special means of defense may be given through means of sexual selection, as the mane of the lion, and the hooked jaw to the male salmon. For the shield may be as important for victory as the sword or spear. Among birds, the contest is often of a more peaceful character. All those who have attended to the subject believe that there is the severest rivalry between the males of many species to attract, by singing, the females. The rock thrush of Guiana, birds of paradise, and some others, congregate, and successive males display, with the most elaborate care, and show off in the best manner, their gorgeous plumage. They likewise perform strange antics before the females, which, standing by as spectators, at last choose the most attractive partner. Those who have closely attended to birds in confinement well know that they often take individual preferences and dislikes. Thus, Sir R. Heron has described how a pied peacock was eminently attractive to all his hen birds. I cannot here enter on the necessary details, but if man can in a short time give beauty and an elegant carriage to his bantams, according to his standard of beauty, I can see no good reason to doubt that female birds, by selecting, during thousands of generations, the most melodious or beautiful males, according to their standard of beauty, might produce a marked effect. Some well-known laws with respect to the plumage of male and female birds, in comparison with the plumage of the young, can partly be explained through the action of sexual selection on variations occurring at different ages, and transmitted to the males alone or to both sexes at corresponding ages. But I have not space here to enter on this subject. Thus it is, as I believe, that when the males and females of any animal have the same general habits of life, but differ in structure, color, or ornament, such differences have been mainly caused by sexual selection, that is, by individual males having had, in successive generations, some slight advantage over other males in their weapons, means of defense, or charms, which they have transmitted to their male offspring alone. Yet I would not wish to attribute all sexual differences to this agency, for we see in our domestic animals peculiarities arising and becoming attached to the male sex, which apparently have not been augmented through selection by man. The tuft of hair on the breast of the wild turkey-cock cannot be of any use, and it is doubtful whether it can be ornamental in the eyes of the female bird. Indeed, had the tuft appeared under domestication, it would have been called a monstrosity. Illustrations of the action of natural selection, or the survival of the fittest. In order to make it clear how, as I believe, natural selection acts, I must beg permission to give one or two imaginary illustrations. Let us take the case of a wolf, which preys on various animals, securing, some by craft, some by strength, and some by fleetness. And let us suppose that the fleetest prey, the deer, for instance, had from any change in the country increased in numbers, or that other prey had decreased in numbers during that season of the year when the wolf was hardest pressed for food. Under such circumstances, the swiftest and slimmest wolves have the best chance of surviving, and so be preserved or selected, provided always that they retain strength to master their prey at this or some other period of the year when they were compelled to prey on other animals. I can see no more reason to doubt that this would be the result than that man should be able to improve the fleetness of his greyhounds by careful and methodical selection, or by that kind of unconscious selection which follows from each man trying to keep the best dogs without any thought of modifying the breed. Even without any change in the proportional numbers of the animals on which our wolf preyed, a cub might be born with an innate tendency to pursue certain kinds of prey. Nor can this be thought very improbable, for we often observe great differences in the natural tendencies of our domestic animals. One cat, for instance, taking to catch rats, another mice. One cat, according to Mr. St. John, bringing home winged game, another hares or rabbits, and another hunting on marshy ground, and almost nightly catching woodcocks or snipes. The tendency to catch rats rather than mice is known to be inherited. Now, if any slight innate change of habit or of structure benefited an individual wolf, it would have the best chance of surviving and leaving offspring. Some of its young would probably inherit the same habits of structure, and by the repetition of this process, a new variety might be formed, which would either supplant or coexist with the parent form of wolf. Or, again, the wolves inhabiting a mountainous district, and those frequenting the lowlands, would naturally be forced to hunt different prey, and from the continued preservation of the individuals best fitted for the two sites, two varieties might slowly be formed. These varieties would cross and blend where they met. But to this subject of intercrossing we shall soon have to return. I may add that, according to Mr. Pierce, there are two varieties of the wolf inhabiting the Catskill Mountains in the United States, one with a light greyhound-like form, which pursues deer, and the other more bulky, with shorter legs, which more frequently attacks the shepherd's flocks. It should be observed that in the above illustration I speak of the slimmest individual wolves, and not of any single strongly marked variation having been preserved. In former editions of this work I sometimes spoke as if this latter alternative had frequently occurred. I saw the great importance of individual differences, and this led me fully to discuss the results of unconscious selection by man, which depends on the preservation of all the more or less valuable individuals, and on the destruction of the worst. I saw also that the preservation in a state of nature of any occasional deviation of structure, such as a monstrosity, would be a rare event, and that, if at first preserved, it would generally be lost by subsequent intercrossing with ordinary individuals. Nevertheless, until reading an able and valuable article in the North British Review, 1867, I did not appreciate how rarely single variations, whether slight or strongly marked, could be perpetuated. The author takes the case of a pair of animals produced during their lifetime, 200 offspring, of which, from various causes of destruction, only 2 on an average survive to procreate their kind. This is rather an extreme estimate for most of the higher animals, but by no means so for many of the lower organisms. He then shows that if a single individual were born which varied in some manner, giving it twice as good a chance of life as that of the other individuals, yet the chances would be strongly against its survival. Supposing it to survive and to breed, and that half its young inherited the favorable variation, still, as the reviewer goes on to show, the young would have only a slightly better chance of surviving and breeding, and this chance would go on decreasing in the succeeding generations. The justice of these remarks cannot, I think, be disputed. If, for instance, a bird of some kind could procure its food more easily by having its beak curved, and if one were born with its beak strongly curved, and which consequently flourished, nevertheless there would be a very poor chance of this one individual perpetuating its kind to the exclusion of the common form. But there can hardly be a doubt, judging by what we see taking place under domestication, that this result would follow from the preservation, during many generations, of a large number of individuals with, more or less, strongly curved beaks, and from the destruction of a still larger number with the straightest beaks. It should not, however, be overlooked that certain rather strongly marked variations, which no one would rank as mere individual differences, frequently recur owing to a similar organization being similarly acted on, of which fact numerous instances could be given with our domestic productions. In such cases, if the varying individual did not actually transmit to its offspring its newly acquired character, it would undoubtedly transmit to them, as long as the existing conditions remained the same, a still stronger tendency to vary in the same manner. There can also be little doubt that the tendency to vary in the same manner has often been so strong that all the individuals of the same species have been similarly modified without the aid of any form of selection, or only a third, fifth, or 10th part of the individuals may have been thus affected, of which fact several instances could be given. Thus, Greba estimates that about 1/5 of the guillemots in the Faroe Islands consist of a variety so well marked that it was formerly ranked as a distinct species under the name of Uria lacrimans. In cases of this kind, if the variation were of a beneficial nature, the original form would soon be supplanted by the modified form through the survival of the fittest. To the effects of intercrossing in eliminating variations of all kind, I shall have to recur, but it may be here remarked that most animals and plants keep to their proper homes, and do not needlessly wander about. We see this even with migratory birds, which almost always return to the same spot. Consequently, each newly formed variety would generally be, at first, local, as seems to be the common rule with varieties in a state of nature, so that similarly modified individuals would soon exist in a small body together, and would often breed together. If the new variety were successful in its battle for life, it would slowly spread from a central district, competing with and conquering the unchanged individuals on the margins of an ever-increasing circle. It may be worthwhile to give another and more complex illustration of the action of natural selection. Certain plants excrete sweet juice, apparently for the sake of eliminating something injurious from the sap. This is effected, for instance, by glands at the base of the stipules in some leguminosae, and at the backs of the leaves of the common laurel. This juice, though small in quantity, is greedily sought by insects, but their visits do not in any way benefit the plant. Now, let us suppose that the juice, or nectar, was excreted from the inside of the flowers of a certain number of plants of any species. Insects, in seeking the nectar, would get dusted with pollen, and would often transport it from one flower to another. The flowers of two distinct individuals of the same species would thus get crossed, and the act of crossing, as can be fully proved, gives rise to vigorous seedlings, which, consequently, would have the best chance of flourishing and surviving. The plants which produced flowers with the largest glands, or nectaries, excreting most nectar, would oftenest be visited by insects, and would oftenest be crossed, and so, in the long run, would gain the upper hand and form a local variety. The flowers, also, which had their stamens and pistils placed in relation to the size and habits of the particular insect which visited them, so as to favour in any degree the transportal of the pollen, would likewise be favoured. We might have taken the case of insects visiting flowers for the sake of collecting pollen instead of nectar, and as pollen is formed for the sole purpose of fertilization, its destruction appears to be a simple loss to the plant. Yet if a little pollen were carried, at first occasionally, and then habitually, by the pollen-devouring insects from flower to flower, and a cross thus effected, although 9/10 of the pollen were destroyed, it might still be a great gain to the plant to be thus robbed, and the individuals which produced more and more pollen, and had larger anthers, would be selected. When our plant, by the above process, long continued, had been rendered highly attractive to insects, they would, unintentionally on their part, regularly carry pollen from flower to flower, and that they do this effectually I could easily show by many striking facts. I will give only one, as likewise illustrating one step in the separation of the sexes of plants. Some holly trees bear only male flowers, which have 4 stamens, producing a rather small quantity of pollen, and a rudimentary pistil. Other holly trees bear only female flowers. These have a full-sized pistil, and 4 stamens with shriveled anthers, in which not a grain of pollen can be detected. Having found a female tree exactly 60 yards from a male tree, I put the stigmas of 20 flowers, taken from different branches, under the microscope, and on all, without exception, there were a few pollen grains, and on some a profusion. As the wind had set for several days from the female to the male tree, the pollen could not thus have been carried. The weather had been cold and boisterous, and therefore not favourable to bees. Nevertheless, every female flower which I examined had been effectually fertilized by the bees, which had flown from tree to tree in search of nectar. But to return to our imaginary case. As soon as the plant had been rendered so highly attractive to insects that pollen was regularly carried from flower to flower, another process might commence. No naturalist doubts the advantage of what has been called the physiological division of labour. Hence we may believe that it would be advantageous to a plant to produce stamens alone in one flower or on one whole plant, and pistils alone in another flower or on another plant. In plants under culture and placed under new conditions of life, sometimes the male organs and sometimes the female organs become more or less impotent. Now, if we suppose this to occur in ever so slight a degree under nature, then, as pollen is already carried regularly from flower to flower, and as a more complete separation of the sexes of our plant would be advantageous on the principle of the division of labour, individuals with this tendency more and more increased would be continually favoured or selected, until at last a complete separation of the sexes might be effected. It would take up too much space to show the various steps, through dimorphism and other means, by which the separation of the sexes in plants of various kinds is apparently now in progress. But I may add that some of the species of holly in North America are, according to Asa Gray, in an exactly intermediate condition, or, as he expresses it, are more or less dioeciously polygamous. Let us now turn to the nectar-feeding insects. We may suppose the plant of which we have been slowly increasing the nectar by continued selection to be a common plant, and that certain insects depended in main part on its nectar for food. I could give many facts showing how anxious bees are to save time. For instance, their habit of cutting holes and sucking the nectar at the bases of certain flowers, which, with a very little more trouble, they can enter by the mouth. Bearing such facts in mind, it may be believed that under certain circumstances, individual differences in the curvature or length of the proboscis, etc., too slight to be appreciated by us, might profit a bee or other insects, so that certain individuals would be able to obtain their food more quickly than others, and thus the communities to which they belonged would flourish and throw off many swarms inheriting the same peculiarities. The tube of the corolla of the common red or incarnate clovers, Trifolium praetens and incarnatum, do not, on a hasty glance, appear to differ in length. Yet the hive bee can easily suck the nectar out of the incarnate clover, but not out of the common red clover, which is visited by humble bees alone, so that whole fields of the red clover offer in vain an abundant supply of precious nectar to the hive bee. That this nectar is much liked by the hive bee is certain, for I have repeatedly seen, but only in the autumn, many hive bees sucking the flowers through holes bitten in the base of the tube by humble bees. The difference in the length of the corolla in the two kinds of clover, which determines the visits of the hive bee, must be very trifling, for I have been assured that when red clover has been mown, the flowers of the second crop are somewhat smaller, and that these are visited by many hive bees. I do not know whether this statement is accurate, nor whether another published statement can be trusted, namely, that the Ligurian bee, which is generally considered a mere variety of the common hive bee, and which freely crosses with it, is able to reach and suck the nectar of the red clover. Thus, in a country where this kind of clover abounded, it might be a great advantage to the hive bee to have a slightly longer or differently constructed proboscis. On the other hand, as the fertility of this clover absolutely depends on bees visiting the flowers, if humble bees were to become rare in any country, it might be a great advantage to a plant to have a shorter or more deeply divided corolla, so that the hive bees should be enabled to suck its flowers. Thus I can understand how a flower and a bee might slowly become, either simultaneously, or one after the other, modified and adapted to each other in the most perfect manner by the continued preservation of all the individuals which presented slight deviations of structure mutually favorable to each other. I am well aware that this doctrine of natural selection, exemplified in the above imaginary instances, is open to the same objections which were first urged against Sir Charles Lyell's noble views on, quote, the modern changes of the earth as illustrative of geology, end quote. But we now seldom hear the agencies which we see still at work spoken of as trifling and insignificant when used in explaining the excavation of the deepest valleys or the formation of long lines of inland cliffs. Natural selection acts only by the preservation and accumulation of small inherited modifications, each profitable to the preserved being. And as modern geology has almost banished such views as the excavation of a great valley by a single diluvial wave, so will natural selection banish the belief of the continued creation of new organic beings, or of any great and sudden modification in their structure. On the intercrossing of individuals. I must here introduce a short digression. In the case of animals and plants with separated sexes, it is, of course, obvious that two individuals must always, with the exception of the curious and not well understood cases of parthenogenesis, unite for each birth. But in the case of hermaphrodites, this is far from obvious. Nevertheless, there is reason to believe that with all hermaphrodites, two individuals, either occasionally or habitually, concur for the reproduction of their kind. This view was long ago doubtfully suggested by Sprengel, Knight, and Kölreuter. We shall presently see its importance, but I must here treat the subject with extreme brevity, though I have the materials prepared for an ample discussion. All vertebrate animals, all insects, and some other large groups of animals pair for each birth. Modern research has much diminished the number of supposed hermaphrodites, and of real hermaphrodites, as a large number pair. That is, two individuals regularly unite for reproduction, which is all that concerns us. But still there are many hermaphrodite animals which certainly do not habitually pair, and a vast majority of plants are hermaphrodites. What reason, it may be asked, is there for supposing in these cases that two individuals ever concur in reproduction? As it is impossible here to enter on details, I must trust to some general considerations alone. In the first place, I have collected so large a body of facts, and made so many experiments showing, in accordance with the almost universal belief of breeders, that with animals and plants, a cross between different varieties, or between individuals of the same variety, but of another strain, gives vigor and fertility to the offspring, and on the other hand, that close interbreeding diminishes vigor and fertility. That these facts alone incline me to believe that it is a general law of nature that no organic being fertilizes itself for a perpetuity of generations, but that a cross with another individual is, occasionally, perhaps at long intervals of time, indispensable. On the belief that this is a law of nature, we can, I think, understand several large classes of facts, such as the following, which on any other view are inexplicable. Every hybridizer knows how unfavorable exposure to wet is to the fertilization of a flower, yet what a multitude of flowers have their anthers and stigmas fully exposed to the weather. If an occasional cross be indispensable, notwithstanding that the plant's own anthers and pistil stand so near each other as almost to ensure self-fertilization, the fullest freedom for the entrance of pollen from another individual will explain the above state of exposure of the organs. Many flowers, on the other hand, have their organs of fructification closely enclosed, as in the great Papilionaceous, or pea family, but these almost invariably present beautiful and curious adaptations in relation to the visits of insects. So necessary are the visits of bees to many papilionaceous flowers, that their fertility is greatly diminished if these visits be prevented. Now it is scarcely possible for insects to fly from flower to flower, and not to carry pollen from one to another, to the great good of the plant. Insects act like a camel-hair pencil, and it is sufficient to ensure fertilization, just to touch with the same brush the anthers of one flower, and then the stigma of another. But it must not be supposed that bees would thus produce a multitude of hybrids between distinct species, for if a plant's own pollen, and that from another species, are placed on the same stigma, the former is so prepotent that it invariably and completely destroys, as has been shown by Gardner, the influence of the foreign pollen. When the stamens of a flower suddenly spring towards the pistil, or slowly move one after the other towards it, the contrivance seems adapted solely to ensure self-fertilization, and no doubt it is useful for this end. But the agency of insects is often required to cause the stamens to spring forward, as Kohlreuter has shown to be the case with the barberry. And in this very genus, which seems to have a special contrivance for self-fertilization, it is well known that, if closely allied forms or varieties are planted near each other, it is hardly possible to raise pure seedlings, so largely do they naturally cross. In numerous other cases, far from self-fertilization being favored, there are special contrivances which effectually prevent the stigma receiving pollen from its own flower, as I could show from the works of Sprengel and others, as well as from my own observations. For instance, In Lobelia fulgens, there is a really beautiful and elaborate contrivance by which all the infinitely numerous pollen granules are swept out of the conjoined anthers of each flower, before the stigma of that individual flower is ready to receive them, and, as this flower is never visited, at least in my garden, by insects, it never sets a seed, though by placing pollen from one flower on the stigma of another, I raise plenty of seedlings. Another species of Lobelia, which is visited by bees, seeds freely in my garden. In very many other cases, though there is no special mechanical contrivance to prevent the stigma receiving pollen from the same flower, yet, as Sprengel, and more recently Hildebrand and others have shown, and as I can confirm, either the anthers burst before the stigma is ready for fertilization, or the stigma is ready before the pollen of that flower is ready, so that these so-named dichogamous plants have, in fact, separated sexes, and must habitually be crossed. So it is with the reciprocally dimorphic and trimorphic plants previously alluded to. How strange that the pollen and stigmatic surface of the same flower, though placed so close together, as if for the very purpose of self-fertilization, should be, in so many cases, mutually useless to each other. How simply are these facts explained on the view of an occasional cross with a distinct individual being advantageous or indispensable. If several varieties of the cabbage, radish, onion, and of some other plants be allowed to seed near each other, a large majority of the seedlings thus raised turn out, as I found, mongrels. For instance, I raised 233 seedling cabbages from some plants of different varieties growing near each other, and of these only 78 were true to their kind, and some even of these were not perfectly true. Yet the pistil of each cabbage flower is surrounded, not only by its own 6 stamens, but by those of the many other flowers on the same plant, and the pollen of each flower readily gets on its stigma without insect agency. For I have found that plants carefully protected from insects produce the full number of pods. How then comes it that such a vast number of the seedlings are mongrelized? It must arise from the pollen of a distinct variety, having a prepotent effect over the flower's own pollen, and that this is part of the general law of good being derived from the intercrossing of distinct individuals of the same species. When distinct species are crossed, the case is reversed, for a plant's own pollen is always prepotent over foreign pollen. But to this subject we shall return in a future chapter. In the case of a large tree covered with innumerable flowers, it may be objected that pollen could seldom be carried from tree to tree, and at most only from flower to flower on the same tree. And flowers on the same tree can be considered as distinct individuals only in a limited sense. I believe this objection to be valid, but that nature has largely provided against it by giving to trees a strong tendency to bear flowers with separated sexes. When the sexes are separated, although the male and female flowers may be produced on the same tree, pollen must be regularly carried from one flower to flower, and this will give a better chance of pollen being occasionally carried from tree to tree. That trees belonging to all orders have their sexes more often separated than other plants, I find to be the case in this country, and, at my request, Dr. Hooker tabulated the trees of New Zealand, and Dr. Asa Gray those of the United States, and the result was as I anticipated. On the other hand, Dr. Hooker informs me that the rule does not hold good in Australia, but if most of the Australian trees are dichogamous, the same result would follow as if they bore flowers with separated sexes. I have made these few remarks on trees, simply to call attention to the subject. Turning for a brief space to animals, Various terrestrial species are hermaphrodites, such as the land mollusca and earthworms, but these all pair. As yet I have not found a single terrestrial animal which can fertilize itself. This remarkable fact, which offers so strong a contrast with terrestrial plants, is intelligible on the view of an occasional cross being indispensable, for, owing to the nature of the fertilizing element, there are no means, analogous to the action of insects and of the wind with plants, by which an occasional cross could be effected with terrestrial animals without the concurrence of two individuals. Of aquatic animals there are many self-fertilizing hermaphrodites, but here the currents of water offer an obvious means for an occasional cross. As in the case of flowers, I have, as yet, failed, after consultation with one of the highest authorities, namely Professor Huxley, to discover a single hermaphrodite animal with the organs of reproduction so perfectly enclosed that access from without and the occasional influence of a distinct individual can be shown to be physically impossible. Cirripedes long appeared to me to present under this point of view a case of great difficulty, but I have been enabled, by a fortunate chance, to prove that two individuals, though both are self-fertilizing hermaphrodites, do sometimes cross. It must have struck most naturalists as a strange anomaly that, both with animals and plants, some species of the same family, and even of the same genus, though agreeing closely with each other in their whole organization, are hermaphrodites, and some unisexual. But if, in fact, all hermaphrodites do occasionally intercross, the difference between them and unisexual species is, as far as function can be concerned, very small. From these several considerations, and from the many special facts which I have collected, but which I am unable here to give, it appears that with animals and plants, an occasional intercross between distinct individuals is a very general, if not universal, law of nature. End of Chapter 4, Part 1. This LibriVox recording is in the public domain.